And so to start with, let's just talk about and review what we're going to discuss today. So we're going to talk about the basic types of statistics. We're going to talk about data type. We're going to talk about levels of measurement or types of scale. And then we're going to talk about how do we use these three pieces of information to help us decide how best to represent our data in a meaningful way. So there's two basic types of statistics. There's descriptive statistics and there's inferential statistics. And the names of what they are describe exactly how you use them. So descriptive statistics are used to describe data. Inferential statistics are used to make inferences. So descriptive statistics are going to be the main focus of what we're going to discuss today. And the easy way to think about how you use descriptive statistics is it's used to provide a snapshot. So it makes your data easily digestible to the end user. So if you were to have 1,000 observations in a data set, you can use descriptive statistics to be able to say, if you have 10 seconds, this is what you need to know about what's in this data. So the way you primarily do that is you do it through either measures of central tendency, mean, median, or mode, to let people know, well, this is where the most of the observations are generally clustered. This is the average, this is the middle point of the data, or this is the most common observation. And we'll talk about these a little bit more in depth later. Sometimes, though, central tendency is just not appropriate because of the type of data you've collected. For those, you're going to want to let the end user know percentages. Where do most individuals or most observations within your data set lie? And so an example of that would be if we were going to look at the class and figure out how many people have blue eyes, brown eyes, or hazel eyes. We wouldn't want to provide a central tendency of that because that's not a meaningful way to represent that data. But a percentage of those with blue eyes, a percentage of those with hazel eyes, a percentage of those with brown eyes, that's a much more meaningful, more digestible way to provide that. So descriptive statistics describe data. Inferential statistics, they are used to make inferences about the larger population from a probability-based sample. And so we see that throughout our lives whenever you think about any sort of political polls that you've ever seen. So if you see a poll that says Barack Obama has a 65% approval rating, and they'll usually say plus or minus 5. What that means is the Wall Street Journal or whoever's conducted that poll has sampled 1,000 people, and they have used the answers of those 1,000 people to make estimations about what the rest of the population likely feels about President Obama. And a good example also is the 538 blog. And so if any of you have ever looked at Nate Silver's 538 blog, all the information that he has on there, all of it is for the most part inferential statistics. So let's look at when to take public transit from the airport. So it's really unlikely that Nate Silver and his staff went through and calculated every single time that every single person went to the Minneapolis airport to figure out when should you take a cab to the airport. That's very unlikely. More than likely what occurred is that he did a sample of, let's say, 1,000, and he used that sample of 1,000 trips to figure out, okay, this is how long that generally takes, and this is when it makes sense to use one form of public transportation over another. And so this is an example of how he used inferential statistics to figure out when that weekly travel time makes sense. Okay, so within statistics, there's different types of data that we can actually collect. So we can collect what's called qualitative data, and we can collect what's called quantitative data. And much like descriptive and inferential statistics, how we know how they're used based upon the name, the data types are no different. So qualitative data is used to describe a quality or kind. So it consists of values that can be separated into different categories that are distinguished by some non-numeric characteristic. And that's the chief thing to note here, non-numeric. So an example that I just used earlier would be eye color. Obviously, that's a difference of type or difference of quality, as in qualitative, but it's not necessarily a difference of count or difference of possessing that quality. So, in varying amounts. So, if you think about the example of green, blue, and brown eyes, you can have people that either possess the quality of having blue eyes or not possess the quality of having blue eyes, which places in that category. But you're not necessarily measuring, in that example, the blueness of those eyes. And there would be inappropriate to say that, having green eyes is necessarily better than having blue eyes. That type of qualitative data won't let you make those sort of statements. Quantitative data, on the other hand, it does work with quantities, as in quantitative data. And so it does represent a count or a measurement. And so it's a consistent value that you have over, examples would be money or time or height or weight. It's something that can be counted, and you can make reasonable statements to say someone who's 64 inches tall is twice as tall as someone who's 32 inches tall. Someone who weighs 200 pounds weighs twice as much as someone weighs 100 pounds. So there's two basic types, qualitative and quantitative. So what I want to do now is I want to give you the opportunity to sort of identify from these examples which ones are qualitative and which ones are quantitative, and to think about why that might be the case. So review these 4 examples, pause the video and think about which ones are qualitative and quantitative, and when you're ready, push start. So go ahead and pause it now. Okay, welcome back. So in this first example here, a person's social security number, that's a little tricky because we think of numbers and we often think, okay, numbers, they're going to be quantitative in nature, right? But in the same way that eye color is really just a type of category, so is a social security number. So let's think about if we have Joe. So Joe has a social security number of 800000000. And Nancy has a social security number of 4000000. And Jill has a social security number of 2000000. So in the same way that the label of Joe just describes the person who possesses the name of Joe, and the name of Nancy describes the person who possesses the name of Nancy, the social security number does the same thing. And so this is really just a label that's being attached to Joe. It's not describing or counting any sort of quantity of possession of a characteristic. It's really just saying that he has this quality. Nancy has the quality of having this social security number, and Jill has the quality of having this social security number. It would be inappropriate or inaccurate to say that because Joe's number is 800 and Nancy's starts with 400, that Joe's number is twice as good or twice as whatever. It's not. There's no numeric comparison between these numbers. So because of that, a person's social security number is really just a qualitative piece of data. So number of textbooks owned by a student. This is actually going to be quantitative data, and it makes sense if you think about it, because if Joe were to have 20 textbooks and Nancy were to have 10, then it is logical to say and meaningful to say that Joe has twice as many textbooks as Nancy does. And so because of that, because you can count and you can possess more of the observation that we're counting, you can possess more or you can possess less of it, and that's a meaningful statement to make. It's quantitative data. The incomes of college graduates. So incomes are also quantitative data because you can count and you can possess more of whatever incomes is measured, and incomes is measuring money, measuring dollars. And so if Joe were to have $20,000 in income and Nancy was to have $40,000 in income, Nancy would make twice as much. That is a meaningful distinction to make. Likewise, if we think about our central tendencies examples before, you would be able, and you would logically try to do this, to look at our class and say, what is the average income for our class? That might be something that you would want to measure. So it would be quantitative. And then lastly, gender. Gender is similar to eye color in that you can be in the category of male, you can be in the category of female, you can be in the category of bigender, you can be in the category of transgender, you can be in the category of two-spirit, and on and on and on. But you would never make a statement to say that being female is, twice as good or twice as much of whatever quality. You either are or you are not in whatever category that person chooses to identify. And so it's appropriate to say what percentage of people are in each of those categories for whatever given data set. But you would never be able to make any other comparisons beyond that, and certainly you wouldn't be able to get any sort of average or anything from those. So Social Security number is qualitative, number of textbooks is quantitative, income is quantitative, and gender is qualitative. So what are the different types of quantitative data that we can have? Quantitative data can be broken down a little bit more minutely than qualitative data, in that you can have quantitative data that can be represented and more finely parsed depending upon what type of data you have. And so it's pretty easy to remember if you think about the decimal point. And so continuous data can go beyond the decimal point. There are no gaps, there are no interruptions, and there are no jumps. So whatever scale you're using, you're not counting the data as individual units with spaces between those individual units. One number flows directly into the other number. And so that we see that sort of measurement on scale. So if you think about temperature or time or height or weight, any one of those are continuous data, or even money, because it's only limited by how you choose to represent it. Each one of those units can be more finely parsed than one unit. It can go beyond the decimal place, so it is continuous. Discrete data, though, is count data. There are jumps between the data point. And so if we think about our textbook example before, if you count number of textbooks, that would be discrete data, because there is no meaningful distinction between a half a textbook or 3/4 of a textbook or 7/8 of a textbook. So you either have one textbook, two textbook, three textbook, four textbook, on and on and on and on. You can count them, but you would never parcel that out below an individual count. And so discrete data, it does have those jumps between them. So just as we did before, I want to give you the opportunity to review the below examples. And as you review them, I want you to think about, is this data discrete or is it continuous, and then why? So pause the video and you're ready, push start, and we'll review them. Okay, welcome back. So the first example is very similar to the number of textbooks. So the number of 1916 dimes still in circulation. You could count dimes, and so you would have 100 dimes or you would have 110 dimes, but you can't have a half a dime. A half a dime is not a meaningful distinction to make. And so in that way, it's discrete data. There are jumps between them. They're individual units that you're counting, and there is no other finely way to parse that between those units. Voltage, on the other hand, is going to be much more similar to height or weight. So if you think about, you can have a 9.5 volt battery. Voltage is not necessarily measured in discrete units. It's continuous data. So what voltage is passing through that electrical line, it could be 11.5 volts. It could be, 1,000,003/4 volts. It could be any sort of amount of voltage that is possible to flow through those lines. The number of eggs is similar to dimes, so you can't have a half an egg. That's an easy way to think about these, is obviously, does it go beyond the decimal point, and could you have a half of it? And so with the number of eggs, you can't have a half an egg, and so it is going to be discrete data. There are jumps. You have 12 eggs, you have 24 eggs, you have 13 eggs, whatever you have, but you don't have 13.5 eggs. That's not a realistic way to represent those. So the time it takes for a student to complete a test. Time can be a little tricky because it can be dependent upon how you choose to represent it. But when we're talking about a time elapsed for someone in such a short interval where it's not likely that it took more than a day, more than likely this is going to be continuous data, because this is going to be measured down to the second and beyond. It can be measured to the nanosecond, and even smaller if you had the capability of doing so. And so this is going to be continuous data. Time can be discrete data if you're saying that you're going to measure something over the course of a day, and you're not going to parse that data any more finely than 1 day's unit, because obviously if you're jumping 1 day, 2 day, 3 day, then you do have gaps in that data, right? And so this really comes down to how you choose to represent the data. And we'll look about this a little bit more in class when we start to talk about surveys, because this can affect how you choose to represent your responses. And so a good example would be if you have a survey, and on that survey you ask the same question: how many hours a week do you spend studying? So we ask our students that question. If we leave it fill in the blank, so if we leave our answer like that and it's fill in the blank, and a student can respond with whatever he or she wants to respond, well, in that way it would be continuous data, right? Because they could in theory say that I study for 6 hours a week. They could say I study for 5 hours and 15 minutes a week. They can say whatever variations of time they want beyond the decimal point, which is 15 minutes here would represent, right? However, if you get asked the same exact question, how many hours a week do you spend studying, but you give them the option of response categories, and you say select one of the following, and those response categories are 1 to 5 hours, 6 to 10 hours, 7 to 15 hours, and 15 to 25 hours. So in this way, we now have transformed what could be continuous data into discrete data, because there are these chunks and blocks of time. There are jumps within the data. This is 1 unit of data. This is 2 units of data. This is 3 units of data. And this is 4 units of data. And so in that way, we've transformed what could be considered continuous into discrete data. So just to recap that, because I know it's a lot to digest, but just to recap that, the biggest difference is discrete data can be counted. It's individual units. There's jumps in the data. And continuous data is not broken down in that way. It goes beyond the decimal point. It can be more finely parsed.